Hello friends, today I want to talk about the quantifiers. Okay, and there are two types of quantifiers. One is universal quantifiers, and second one is the existential quantifiers. So before we begin with quantifiers, before we understand what is quantifiers, let us understand why we need a quantifier. Okay. So far what we have done is we understood the prepositional logic, the simple statement that contains true or false value. Okay. And those simple statements can be represented using simple variables like P or Q, R, and so on. So we just represent these variables, which actually represent some statement, which could be true or false. We don't know. Okay, that can be anything. So now we know the variables. We can make statements based on variables, which is called the predicate functions, which we learned in the previous video. And if you haven't watched that video, I suggest you to go ahead and watch the video and understand what is predicate logic is, and then come back to this video and continue. So for those who have not gone through the video, let me just reiterate that P of X is a statement which is true or false. It could be true or false, anything, depending on the kind of input you are giving. So if this represent statement such as x is greater than 10, it's a very simple statement. And if you switch some value, give some value to x, for example 1, then the statement is false. And if you give the value as 20, the value of x is 20, then the statement is like this: 20 is greater than 10, which is true. So in any case, you can see that x comes from a particular, or you can say, this statement can be written as P, and then we put value x1. Okay, I'll just keep adding it, and then I add one more true value, x2, and then I again add one more statement like this P, and value of x is x3, and so on. I can say n value in this predicate. If I put n value in this predicate, what happens is, if all of them are true, for example, every single value is true, then what happens is I get it true. The entire the list of all this expression involving so many values, this expression will result in true. If any one of the value, if one single value is false, say for example this value is false, let me pick another color. So if I say one value is false, then the no matter what the outcome of the other values, even a single false will make this entire expression false. Okay, so I can make an assumption, I can make a statement about the x, that x comes from a domain, x comes from a universe or a domain say for example f comes from a domain D, and I can say that for all value of x, for all x, for all x, and if all x, if this statement is true, if for all x p of x is true, p of x is true. Okay, so this is called universal quantifying. I am taking x from a particular domain, and for all of x, the predicate is true, which means I am making a universal assumption of the universal assumption on the x. I'm assuming that all the, or in fact I'm saying that I'm making a claim that x from the domain D, for all the x in the domain D, the px, the predicate is true. This is true. And not even a single item, I don't have a single value which gives me false. For example, here I am given x3, so I don't have any single item which I can input here and the predicate is false. So this entire expression like this, whatever x from the domain I take, and if I put it in the predicate, it gives me a true value, and therefore the entire expression is true. Okay, so there is another way of writing this. Okay, there is a much simpler way of writing this, and that is called universal quantification or universal quantifier. Okay, so which I am going to do right now. So I will write the statement, I will write the same statement, in a different way, a much simpler way, which we can use for computation. So what I can do is, so let's say x belong to a domain, D. This is for sure because x always comes from a domain. Okay, if x is a number, it comes from some domain, natural number, whole number, or real number, a rational number. So many domains are there if x is a number. And this x, I can say for all x, this is the way to represent x. This is universal quantification of x. For all x, okay, p of x is true. So that I simply write like this. So I'm saying, I'm making a claim that whatever x you choose, and if this x, if you take this x and switch here in the predicate, then I'm going to get some value which is true. I'm going to get true, whatever value you put. Very interesting. But so this universal quantification, or universal, I can say universal quantifier, universal quantifier, this universal quantifier can become false also if if we have a counter example, if there is a counter example, there is a counter example, which means I am trying to say that there is an x in domain D, for which P, let's call this as P of I is, if this particular P of xi is going to give me false, then that universal existence or universal quantifier P of x also becomes false. This is the only case when it becomes false. Okay, I said x of I because there could be more than one value, x, 3, 4, 5, I could be anything. So I'm assuming that from the domain I can take any x, and for some x, if the predicate become false, then we can say that the universal quantification is false. Okay, so right now this is true, but it can become false if one of the value P of xi is false. So at least one counter example if I get, then I can say that it is false. So let's see some example. Let's look at some example here. Let us take an example. So earlier there is let's say my x is a real number. Okay, that x belongs to the domain real number, which is normally represented as R, comes from a real number. So real numbers are all regular numbers, okay, that include rational number, irrational number, whole number, okay, negative, positive, fractions, all kind of number comes under real number. So in short, you can say numbers, all numbers. So if x is some number, and that universal quantifier, I am making a claim that x, for all x, P of x, means it's true. For all x, the predicate is true. But what is this predicate? What is this P of x? So the P of x is, what is P of x? Is, let me take something very simple. Say x square is greater than or equal to x. This is a very simple one. So if you try to switch some values here, for example, if you give 2, then 2 square is greater than or equal to 2, right away become false. Because this is 4 and then it's greater than 2. So no, this is true because the reason it is greater than 2. So it is true. So say some less value, we can take less value. So 1 square, we take 1 square greater than equal to x, which is 1. 1. This is also true because here it is equal, so this is also true. What about 0? What about 0? So 0 square is greater than equal to 0. Yes, it is true. So what if I take a fraction like 1 by 2 and then square it? If I take 1 by 2 square and say greater than or equal to 1 by 2. So you know why I'm saying 1 by 2? It's a rational number, so rational number belongs to the real number. Okay, so x value 1 by 2 is acceptable. It is something that we can accept here, and see that this is 1 by 4 is greater than or equal to 1 by 2. Here the statement becomes false. So basically, whenever the number is a fraction and you square it and then you compare it with the x, it's not going to work. So there is a counter example. So we have to avoid all the fractions, because this will not work for the fraction. So our domain need to be changed. In mathematics, this is how in mathematics we fix the problems, fix the theorems, because we have to find the correct domain. If we don't have the correct domain, then our function or equation will not be satisfactory. It won't satisfy it. Here we have a simple expression, but it will not be satisfied unless we fix the domain. We select the right thing for the domain. So if I say if x belong to integers, just the integers, then I can say that this is correct. So how this will work? If x belong to integers and which is symbol z, this is symbol for integers. Okay, so let me correct this. If x belong to x is an integer, which means only whole number like -1, 0, all negative numbers, and then 1, and all positive numbers. If I take any of these infinite positive and infinite negative number and 0, then my expression is right, because let's say x square is greater than or equal to x. So what happens if I switch -2 and take a square? -2 square greater than equal to -2. Does this works or not? So what I get is the +4, because negative is positive, so I get +4, which is obviously greater than -2, much higher than -2. Okay, so it works for a positive number, it works for negative number, it doesn't work for the fractions. Okay, it doesn't work for the fractions and some kind of numbers. So our domain is limited to, we must fix the domain, limit the domain to integers. If domain is from integer, there is universal quantifier for all x, the predicate x square greater than equal to x, it works. Then I can say it is true. Otherwise it will be false. So hope you understand what it means. Let us see another example. Let's take one more example. So let me just wipe this thing. So this time x is again x belong to the x belong to real number. So no, let x belong to the integers. Okay, for convenience we just take integers. Then we make a universal claim, universal quantifier. We can quantify it like, for all x, e of x, or the predicate function px, for all x, okay, the claim is that x square is greater than 0. So if we switch all numbers, like if we say, for example, if we switch negative numbers, what I'm going to get is 1 greater than 0, which is true. So this is true. So if you take positive number like 2, x value is 2, then I get 4, and it is greater than 0, which is also true. What if I take x equals 0? If I take x equals 0, what happens is that I get 0 greater than 0. So you see that my domain doesn't work for x. For all numbers, maybe for fractions, let's see fractions. If I say negative 2, 1 by 2, if I do fractions, 1 by 4, if you square 1 by 2, I'll get 1 by 4, which is greater than 0. So it's a good thing that it works for rational numbers also, and even negative rational numbers. Let's see if we have a negative rational number, 1 by 3. Negative rational number will give me, again it give me positive number, 1 by 9, which is obviously greater than 0. So this is true. So basically it works for all the numbers, okay, except 0. So it works, domain works for all numbers, all real numbers, okay, except 0. So how can I write this universal quantification? So I can write this as, I can write the domain as x belongs to R, that is real number, and plus x is greater than 0 and x is less than 0. So you get the idea, right? It means that we must limit x to something that it is either positive or negative. So I hope you learned something today, and with that, I'll see you in the next video. Thank you very much.